The next experiment is Michelson interferometer. The objectives of these experiments are first assembling a Michelson interferometer, second to observe the interference pattern, and finally determine the wavelength of the light of a helium neon laser using a Michelson interferometer. There is a famous experiment, Michelson-Morley experiment, and in this experiment Michelson wanted to prove the existence of ether, and for doing this experiment he made a setup called Michelson interferometer and performed the experiment in the on the surface of the earth, on the top of the hill, and in many other places also. And the null result of this experiment, that is, it was proved after this experiment that ether does not exist. So the null results of this Michelson-Morley experiment leads to a new mechanics. Okay, so this is the setup they have used. You can see the picture of the experimental setup that is used in our lab, and parts of the experiment is written here. So the parts are A, B, C, D, E, F, G, and H is marked in this picture. So A is the laser source. So here we will use helium neon laser source. B is the beam divider. So it actually partly the light is getting reflected and partly it is getting transmitted. Okay, so this is the beam divider. So one single beam is an incident in the beam divider, and this beam is divided into two parts. One is partly reflected and one is partly transmitted through the divider. Okay, so C and D are the mirrors. So D is a separate mirrors. So from the beam which is reflected through the beam divider, so it is incident on the uh, mirror D, and it reflects back. Okay, and mirror C is attached with the another setup. Okay, that will I'm coming later. So E is the spherical lens. So the lights which has been received um, through the reflections and the transmissions to through mirror D and C, that will be received in the spherical lens and will get the interference pattern in the screen. F is the fine adjustment mechanism and G is the reducing gear for fine adjustment mechanism. Okay, so if we rotate the reducing gear, that is G, so with the change in F, the change in the scale of F will be very small. So suppose of hundred of rotations will make a single digit single digit translation in F. So by this way we can get a smaller transition in the change of the mirror. And H is the screen where we can see the interference pattern. Now how the Michelson interferometer operates. So the laser beam the laser beam is coming from the helium neon laser source, and it will incident on the beam splitter, and it will be divided into two parts. One is reflected to the mirror D, and one is transmitted to the mirror C. Okay, so the light which is been incident to mirror D will be reflected back, and it will transmit through the beam divider to the spherical cell, and the beam which is been transmitted from the laser beam laser source to directly to C, that will be reflected through the beam divider, and it will come to the uh, spherical lens. So if the angle of the beam divider is 45 degree, then the beam which is been incident from the laser source to the mirror D, that will be normal, and again the beam that will be that is reflected through C, and which is been transmitted through from mirror D to the spherical cell will be normal as well. Okay, so the in the spherical lens, the beams will be collected. Okay, and the beams which is been reflected from the mirror D, and it is transmitted through the beam divider, and coming to the spherical lens, and which is been uh, and the beam which is been reflected through mirror C, and it will be reflected by the spherical beam divider, that will get interfered, and during this interference phenomena, many multiple reflections and multiple transmissions will occur, and finally we will get the interference pattern in the spherical through the spherical lens in the screen, which is called translucent screen. So this is the mechanism of the Michelson interferometer. The schematic diagram of this Michelson interferometer uh, is here for your understanding in a better way. So the laser is coming in a beam divider. It will reflected to a mirror, and transmitted to another mirror, and the beam is reflected back from the mirror, and it will be transmitted through this beam divider, and this mirror which is attached with the uh, reducing gear mechanism. So that is from that mirror, the beam is reflected back to the beam divider, and it will be reflected again to the spherical lens, and thus in the spherical through the spherical lens, the beams are collecting, and they will get interfered, and the interference pattern in the screen will the uh, look like this as in this picture. Okay, so due to the rotations in the gear reducing gear mechanism, so there will be a displacement in the mirror attached with this mechanism, right? This displacement is taken as delta S. So with a single rotation or single revolution of this reducing gear, the displacement will be 5 micrometer. So when there is n revolutions in the reducing gear, so this displacement will be 5 micrometer multiplied by n, capital N. Now suppose the wavelength of the light is lambda, and capital Z is the number of counted intensity maxima when the rotation occurs at a particular point of in the screen. So we have to mark a point in the screen, we have to mark a maxima intensity in the screen, and during rotation we have to count what will be the number of counted intensity maxima during the rotations or revolution. Suppose we have rotated in the first rotation of this reducing gear, the number of intensity maxima counted in a particular marked point in the screen, that is 16. Okay, so capital Z is 16 for n equal to 1. And if we rotate again, suppose the value is 33. So 33 is the capital Z. So in a particular marked point, this the intensity maxima has displayed 33 times. So so this is the capital Z. Now, if the wavelength is lambda, then we can say that capital Z multiplied by the wavelength of the light, that will be equal to the displacement of this reducing gear multiplied by 2. So this 2 factor has come because of the fact that the paths are counted twice. One is for incident light and another is for the reflected light. So capital Z multiplied by lambda will be 2 into delta S. So from this equation, if we count capital Z and we know delta S, so we can easily measure the value of the wavelength of the incident light beam, incident laser beam. So this is the Michelson interferometer. So we'll demonstrate this experiment in the upcoming lab session. Thank you.